Alright, so after we have defined all those terms, angular displacement and angular velocity, we considered whether such circular motion is natural for objects or not. And we found that for an object moving in a circle, right, it can't possibly be in equilibrium because it's not moving in a straight line. Newton's first law says that an object needs to be moving in a straight line at uniform speed or at rest being considered at equilibrium. So the natural conclusion of this is if you're moving in a circle, it is definitely true that you must be undergoing some kind of acceleration. And that acceleration is the one that would change the velocity direction so that the velocity is now moving like a circle rather than a straight line. So that was our conclusion from the last lecture. Right? We considered an argument where if the acceleration was in the direction of motion at any instant, object would speed up. And if the acceleration was opposite the direction of motion, it would slow down. But for our object is moving in its uniform circular motion, it is neither speeding up nor slowing down. It's just maintaining a constant speed moving in a circle. Right? So if that's true, it can't possibly be that the acceleration has a component in the direction of motion. So that's why we concluded that the acceleration must then be perpendicular to the direction of motion. Right? So we came up with a vector diagram that looks like this. We have a velocity that's always tangent to the circle, and an acceleration that's always perpendicular to the tangent to the circle, which in other words is radial direction. It's in the direction of the radius. So I tested y'all also. Is this acceleration a constant acceleration? Well, y'all said that yes, it's constant. But it's only constant in magnitude, but not constant in direction. Since pointing towards the center is a changing direction in the first place. Whenever the object moves, the vector that points towards the center must change as well in order to point towards the center. So the acceleration direction is also changing, but not its magnitude. So that's what we did the last lesson. And I did a quick derivation on what the expression for the centripetal acceleration should be using a geometric argument. Right, let me quickly summarize the argument for you. Now, we consider an object moving through a small arc PQ. Yeah, okay? Right, if we consider an object moving through a small arc PQ, we can draw a simple geometrical diagram with PQ and O, the center of the circle, where PQ is delta R. We call a small distance delta R. So it forms an isosceles triangle with the sides R. Right, at the same time, at P and at Q, the object must have an instantaneous velocity. And that velocity factor is given by VI and VF. So we are going to consider a second diagram looking at VI and VF. And noting that since the speeds are the same, but the directions are different, they must form again an isosceles triangle, with the third side being what we call delta V, the change in velocity, which is VF, this vector, minus VI, the other vector. Right? So these two triangles, when we put them together, we realize that they are similar triangles because they are both isosceles triangles with the same common center angle, which means to say that the ratio of the side to the short end must also be the same for both of them. So we'll claim that delta V over V must be delta R over R. Alright? So what's good? Now what was the objective of all this? It's so that we can find an expression for acceleration. And acceleration is nothing but delta V over delta T. So that was why we wanted to compare this. We wanted to find a way to express delta V as a ratio of radius, because radius is something we know in circular motion, the radius of the circle. So once we compare these two similar triangles, we'll find that we can express delta V as V over R delta R. Right? So V is the velocity, R is the radius, and then delta R is the small change in distance when you move from P to Q. Right? So far so good? People at the back, you alright? Okay, so the most crucial part of this geometrical argument comes in the next step. I'm going to say that this delta R, although it's a line joining P to Q, is going to be equal to the arc length, but only in the case where the distance P to Q is very small. So the length of the chord is now the length of the arc. Right? So if I can make that claim, I can replace delta R, which is still useless to us, with delta S. And delta S is something we want, because delta S is the arc length. And we've got delta S over delta T, and we know that delta S and delta T are very small. It just becomes ds dt, which is nothing but the rate of change of displacement, which is speed. So you get one more v from this term here. So acceleration becomes v squared over r, which is a very simple expression for acceleration, right? V is the speed of the object in circular motion, and r is the radius. So the acceleration somehow is now dependent on the velocity and the radius, instead of some complicated expression that we don't expect. So it becomes very simple. So this derivation is called a geometric argument. It is not required for A-level. That means we won't be tested on deriving this from scratch. Okay, we can test it to you step by step, but we cannot test it to you one shot. Hey, please derive this for me. Alright? So, well, the most important thing you need in A-level is the most important thing you need in A-level is this expression. A equals to v squared over r. Right? Now, we also learned one more expression earlier on in lecture 1, which is v equals to r omega. The velocity is the radius times the angular velocity. So we can get one more other expression for centripetal acceleration that doesn't have velocity, but instead has angular velocity. So these two equations are equivalent. Right? It depends on which one you need in the context of the question to solve. Right? So A equals to v squared over r, or A equals to r omega squared. Okay, either is fine. So, coming back to the idea of an object being not at equilibrium moving in a circle, we know that it requires an acceleration. But if you have an acceleration, a force must be causing an acceleration, right? So, if we are undergoing acceleration in a circle, there must mean there's a force causing my object to move in a circle. We will call that force the centripetal force. So it's a result of Newton's first law, right? It's still again a result of Newton's first law. Since my object is moving in a circular path, it is not linear. If it's not linear, a force must be responsible for this change, and it must be undergoing a net force in order to move in a circle. And that net force is what we call the centripetal force. It's related to the centripetal acceleration, which we just derived. So what exactly is this centripetal force? Is it a brand new force like tension or weight that you are learning about? Well, when we draw free body diagrams in dynamics, right, we will draw in all the forces that we can identify: upthrust, weight, tension. But we will never draw in this other force that you all will get, which is the sum of all those forces, called the net force. You don't draw it in because the net force isn't an actual third force. Right? And the net force is just the sum of the existing forces acting on the object, which we'll use to go and calculate its acceleration in dynamics. So we don't normally sketch in the net force. So in this case, for circular motion, the centripetal force is nothing but the net force. So the centripetal force isn't a new force that you're learning. The centripetal force is just going to be the net force that the object moving in circular motion is experiencing. Which means to say that it's not a special force. It's just a result of existing forces that you already know in the situation. Okay, the rest of the examples today, you will see what I'm talking about in specific cases. Right? So what's special about centripetal force then? Well, it's a special case where the net force points towards the center of the circle, as opposed to any other direction in dynamics. Okay, and one more thing we can observe about this net force is normally forces can do work. You're probably doing work energy power tutorial right now, right? And we know the work done is force times distance moved. However, this force, this centripetal force, because it's always perpendicular to the velocity, the object will never actually do any work. After it has moved one step, the force is again perpendicular to the velocity. So it won't do any work. Because you need to move in the same direction of the force in order to do work. So as you move in a circle, no work ends up being done. Right? It makes sense energetically because your object is not gaining Ke. So there's no work done on it. Right? It moves in a circle, but its Ke never changes. Only the direction changes. So a centripetal force will never give you additional energy because it doesn't accelerate the object, so you don't gain Ke. Right? And we can tell that it's immediately true because the vectors for velocity and the vectors for the force are perpendicular to one another. So it's not possible for your work to be done because the force is never in the direction of motion. So it's perpendicular to it. So there's a few special notes about the centripetal force. Alright, maybe I'll think about that for a while. Anyone has any questions? Don't be shy. Okay, if not, we'll derive the expression for centripetal force. It's not going to be a long derivation. It's simply going to be centripetal acceleration times m, because F equals to ma. So it must be true in this case as well. So the centripetal force is just mat, which is mass times centripetal acceleration. So our existing formula for centripetal acceleration, v squared over r, now becomes mv squared over r. And the existing equation for r omega squared simply becomes mr omega squared. So it's quite simple. It's just somehow dependent on the mass as well now, the force. Right, so our vector diagram could look something like this. This is the velocity. And the centripetal force, of course, must be in the direction of the centripetal acceleration, which also points towards the center. That's all. So if we know about, well, we visit Newton's first law about times already. So we know that this object moving in circular motion, right, must have some force causing it to be moving in circular motion. Now, I would like you all to compare the case, right, where we are moving in circular motion and we suddenly remove this force at this instant in the motion. So I'm not sure if you all behind can see the contrast is a bit low. There's a circle here, and this circular object is moving in a circle, and it has a velocity v at this instant. And of course, the centripetal force points towards the center. What would happen to this object if I immediately remove the centripetal force? Which is, I immediately remove the resultant force. Would there be any forces acting on this object if I remove the resultant force? No, that's what resultant force is, right? The net force. So now no net force. Well, since there's no net force, nothing changes the direction of the object. So if it is moving tangential to the curve at this point, it must continue to move tangential to the curve. So watch out for the animation. We show the ball moving off in a straight line with the velocity it had the moment the force was removed. So this is what we call moving off in a straight line after you have removed the resultant force. So it's just a perfect example of an object in Newton's first law. Right? It's moving off in a straight line with constant velocity since there's no more force to change its direction. Right, so this is a necessary truth for objects in circular motion if we somehow remove away the force. Alright? Okay, so let's recap a little bit. In order to move in a circle, we need an acceleration. The acceleration is v squared over r or r omega squared. And to get this acceleration, we need a force, which is nothing but the resultant force. So it's mv squared over r or mr omega squared. That's all. Right, I actually still haven't shown you an example of what a real centripetal force looks like, right? So before we do that, what we call doing those is just solving centripetal motion problems. I can give you a short guide on it, which is to draw a free body diagram. Right? So drawing a free body diagram involves sketching out the object separate from any other object, labeling all the forces you know act on the object, tension, weight, friction, normal force, all must be sketched out. Right? Then you need to label the radius of motion, because you know it's moving in a circle, right? Just label where the radius is. Resolve your forces. Try to find forces that are towards the center of the circle and perpendicular to the center of the circle. And then apply Newton's law for each axis. Because it's moving in a circle, the net force must be our centripetal force, and any other force that's perpendicular to the center must be zero. Right? Because it's neither accelerating nor decelerating. So once we set up these equations, we can solve simultaneously to get the answer. So that's in principle what we'll do for all circular motion questions. Set up two equations, one for y-axis, one for x-axis, and solve. So that's an idea, but it's quite abstract. So we'll look at it in a few examples, alright? So not too different from a dynamics problem solving. Right? In dynamics, you also do the same thing. Draw free body diagram, form two equations, solve. But in this case, we have the extra step of identifying the radius. So, simplest example, Earth orbiting the Sun. So if Earth is orbiting the Sun, what is the only force acting on Earth? It is nothing but gravitational force. The Sun's gravity pulls on the Earth, and the direction of that force is always towards the center. So voila, the gravitational force is the centripetal force, because the gravitational force is the resultant force. No other forces act on Earth, so no other forces is needed to be the centripetal force other than gravity. So what's the radius of motion? Well, it will be the Earth-Sun rate distance. And what will be the speed of motion? It will be the speed at which the Earth moves in its orbit around the Sun. So if you want to draw a free body diagram for the Earth, it will be like that. Just draw the Earth, draw one vector pointing towards the Sun. That's the centripetal force. So how will my equation look like? I would say that Fg, the gravitational force, will be equal to Fc, the centripetal force. So of course you all don't have an expression for Fg yet, because that's the next chapter. Okay, you'll learn Newton's law of gravitation next. So that will be where you plug your Fg in. But the right hand side, the Fc, will be this one. So for example, if we knew all the quantities that make up the gravitational force, we would then be able to determine the speed in which Earth moves around the Sun, and also the period in which Earth moves around the Sun, which actually you all know, because it is 1 year, right? That's the period in which the Earth takes to move around the Sun, right? Exactly 1 year. Right? So actually you'll be able to estimate quite a lot of information with the general knowledge that you all have. Okay, the Earth moves around the Sun. That's one form of circular motion. But all of us are also in circular motion now, right? In addition to the fact that we are on the Earth and the Earth moves around the Sun, each of us is in circular motion around the Earth as the Earth rotates one time on its axis, especially us in Singapore, we're at the equator. So sitting on the equator, we'll go around the Earth exactly once every 24 hours. So there's a circular motion associated with our planet's rotation. Where do you think, okay, so we are moving in circular motion, where do you think the force that causes us to move in such a circle comes from? What type of force is it? Do you think it's tension? Do you think it's friction? It's gravity, right? So same like the Sun, it is gravity that causes us to move around the Earth once every 24 hours. So we know the period of an object moving around the Earth because it's exactly 24 hours. The Earth rotates once every 24 hours. Okay, we can calculate the acceleration due to this rotation. So using the formula for centripetal acceleration, I want you all to go and calculate this acceleration for people on Earth. Okay, the piece of information I'm giving you is the Earth's radius is 6370 kilometers. So once you've done that, right, you can go and try calculating the same thing for someone on the equator of the planet Jupiter. Right? The Jupiter's period is 9 hours 55 minutes. Okay, give this example a try. Okay, we have a very good question there. In the equations, the quantity represented by v, right, is it velocity or speed? Or what do you think it is? It's actually speed because the direction can't be represented in the equation so simply. Right? Because the direction constantly changes. So it just represents the speed of the particle, which is always constant for uniform circular motion. How do we know the direction? Well, we just check which part of the circle it has, draw the tangent, that will be the direction of the speed, which then will give us back our velocity if we need it. Right? So most of you were able to do this question. Some of you were able to solve it in one equation, some of you took 2 or 3, but it's all the same. Of course, solving questions quickly is advantageous. So if you recognize that straight away, you can use A equals to R omega squared and substitute omega as 2 pi over the period. You should be able to get your answer of 0.0337 meters per second squared. We are expecting something else. We're expecting another number. So this is the centripetal acceleration associated with us moving in a period around the Earth. Right? This is not 9.81, the gravitational acceleration of free fall. Now, shouldn't they be related? After all, the gravitational acceleration is what's causing us to have our weight. And weight is the gravitational force, and the gravitational force is also responsible for this. Right? Well, if we draw a free body diagram of any object actually performing this 24-hour rotation like you and me, this is actually what the forces will look like. Right? First, there's a gravitational force pulling us down towards the Earth. But because we are also sitting on the chair, right, the chair exerts an upward normal force on us. Which means, on a normal day-to-day basis, if we are not considering our circular motion around the Earth, we just say they are equal and we are balanced. But we're not. The gravitational force must be slightly larger than the normal force, so that we end up moving once around the Earth every 24 hours. Do you all get that? Then I will explain it a different way. Now, think about the force of gravity producing an acceleration on us. Now, part of the acceleration is used to keep us moving in a circle. Right? So, for example, if you release an object in mid-air, alright, part of the gravitational force exerting on an object released in mid-air is used to keep that object moving in a 24-hour circle around the Earth. But the remaining part of it, which is most of it, 9.77 at the equator, that will be used to accelerate you down to the ground. So you can say that the force has 2 parts. One part to keep you moving around the Earth, and the other to help you accelerate down to the ground. Now we don't have a choice on the 24-hour part, because the Earth rotates at its fixed speed. So that's why there's that part that must be taken care of. Then the remainder is how fast you accelerate to the ground. Alright, anyone has any questions on that? Yes, Patrick? That's exactly it. So our apparent weight is not actually the gravitational force. It's minus away whatever impact that circular motion has on us. But we still need to keep moving in a circle, and we cannot negate this small but non-zero quantity here. But it also tells you why there's a difference in G measured in different countries, right? We use G equals to 9.81 in your examinations, which is determined by Cambridge. Cambridge is in England. Right? Even England don't take such a big circle to move around the Earth as we do because they're actually at a higher latitude, right? Yeah. And we are at the equator, we move through the entire radius of the Earth. So a person at the North Pole will not need to move through any circle at all. He'll just rotate about his spot once every 24 hours. You won't feel it, but he does do it. Right? And the further you go from the pole to the equator, the bigger the circle you have to produce. So, although this effect is very small, okay, you can discuss with the person beside you who is more likely to die, a person who jumps off the first floor at the equator or a person who jumps off the first floor at the North Pole. There will be a difference. What's the difference? Who is more likely to die? Yeah. At the equator, right? But a very negligible amount now. It's just a very small effect, that's all. Right? So moving the circular motion uses up part of the gravitational force. So if you're interested, the expression for our g gravitational acceleration due to free fall g is actually not using gravity alone, but rather the force of gravity or the acceleration due to gravity minus away the acceleration required for circular motion. So this is the full expression. You don't need to memorize it. You'll get this part from gravitation. This part comes from gravitation, which is next topic. Okay, so we use Newton's law of gravitation to get the amount of acceleration we should be experiencing if we were at the North Pole. This is the amount to take into account if we were at the equator. Okay? Not something you realize, right? But now you can account very quantitatively for the difference between G at different parts of the Earth. Okay, we've already done part of the question. I still ask you all to do the same calculations for Jupiter, right? So, most of you would have been able to use the same equations to get a value of 2.21 meters per second square, which is almost 100 times or more than less than 100 times of that on Earth. Right? That's because Jupiter is so massive, and even though its radius is so large, the effect is very large. Right? But that's not the main reason. The main reason is that Jupiter has a very, very, very fast period. One day there is only 9 hours 55 minutes. Well, how many school periods can we cram into that, man? I think the sky will go dark and bright one time when you're in school. Right? Because it's 9 hours 55 minutes. So that's also another reason, right, why you look at Jupiter and see all these bands. Because it rotates so fast, it pulls its clouds into bands. On Earth, we don't have such fast rotation, so we got fluffy clouds. Right? Well, on Jupiter, because it rotates so fast, it pulls its clouds into bands, among other reasons. Right? So pretty cool. Right? This effect, right, of spinning very fast also partly accounts for the difference in bulging of the planet. On Earth, right, the equator is slightly thicker than the distance from the center of the Earth to the North Pole. But that effect is very small. For Jupiter, the effect is much larger because of this spinning effect. So it tends to spread the material out a little bit more, so it bulges out this way. So we can say that the value of G is lower at the equator, both because of circular motion and because the bulk is larger, reducing the gravitational force there as well. So there's two effects that account for a smaller G at the equator on a large planet like Jupiter compared to Earth. Right? Alright, that's just some tidbits for y'all. Okay, anyone has any questions? Okay, enough astrophysics, back to Earth. Now, quite a lot of you have been, okay, most of you are Chinese people, so you eat at Chinese restaurants, and Chinese restaurants are big round tables, right? And in big round tables, it's very difficult to get the vinegar across the table for the other person to put into his soup, right? So what do we need? You know the name of this device? It's a big circular plate that you put on top of the table and you can turn. It's called Lazy Susan. Heard of it? Yeah, lucky no one gets called Susan, right? So it's called Lazy Susan. It allows you to transfer plates from one side of the table to the other or anything on the table. But how does this device work? It doesn't make sense, right? We just discussed that if you're moving in circular motion, you're going to need a net force acting on the object. And clearly it's not a gravitational force causing your plate to move in a circle. And if you try to move the plate, you accelerate it. Newton's first law would say that the plate would fly off the Lazy Susan. That makes sense, right? So if you give it instantaneous velocity, all it will do is just fly in a straight line because no other force keeps it moving in circular motion. Yet the Lazy Susan works. So there must be a force responsible for that. What do you think it is? Why are you so smart? Seriously, you did the notes. Okay, just kidding. You are smart. So it is friction, right? Because there's friction on the plates, the friction now becomes the centripetal force that provides the centripetal acceleration to help you move in a circle. So no longer gravity, now it's friction. So many different forces can take the place of the centripetal force as long as it always acts towards the center. So we can say that friction is now the centripetal force. So it also has this form mr omega square mv square over r. Now, some of y'all would be thinking a little bit fast right now. You'll be thinking, hey, how do I know that the friction must always point towards the center of the circle? After all, doesn't friction oppose motion? And if the object is going to move in a straight line, shouldn't motion be in the opposite direction, not towards the center of the circle? But to understand this, you need to imagine yourself in the center of the circle. So imagine you're in the center of the Lazy Susan. And if a plate flies off the Lazy Susan as you are spinning, what direction do you see the plate flying off in? Is it tangent to you? No, it won't look like a tangent to you. It will look as if the plate is moving away from you in the radial direction. Right? Because you're also spinning at the same time. So you already account for the linear motion. What you will see is the plate moving away from you. So that's why the motion of the plate is to tend to move out of the circle. The friction must be back towards the center of the circle. So the friction is still opposing motion, as you would expect. Okay, take a minute to process this. Imagine yourself in the center of the turntable, and as you turn the turntable, the dish flies off the turntable. Will it fly in a tangential or in a radial direction from your perspective? Here, you want to convince yourself. The friction must point towards the center at all times. Okay, so we figured out how planets move. We have figured out how people remain on the Earth and rotating around the Earth once every 24 hours and not disappear into space because the Earth is rotating, right? We've also figured out how plates stay on the Lazy Susan, which you can negate, by the way. This is friction. You can reduce friction by spraying those kind of anti-friction material on top of your Lazy Susan, and then you can see plates fly off. It's very funny. You rotate and then you see the plate fly off. You know. Wait. I'm sure you have seen like doing wedding dinners, right? When the condensation of the cup is too much, and then there's very little drink left in the cup, and you put the cup on it, and you try to turn it, the thing will try to fly off the turntable. So that's the same effect. Because friction is responsible for circular motion, if you can remove the friction until it's insufficient, the object will no longer be able to stay in circular motion. Now we're going to see a very similar example here. Alright? In this case, we have a ball being poked in a horizontal circle. So I'm sure you have done this sometime in your life with some object. You take a string, you twirl it in a circle. Right? That's circular motion as well. Right? Who's providing the centripetal force in this instance? Thanks. It's tension, right? Because it's a string. So tension is solely responsible for circular motion. Right? So let's consider this example. We have a ball of half kilo attached to a super long 1.5 meter string. Okay, this is like some Olympic sport, right? It's not short put. I said this in another lecture and they corrected me. It's not discuss, right? Because there's no disc. Yeah, but y'all know there's like a cannonball and then they hold and turn, and then they throw it. Right? That's the example of that. Right? But the problem with strings, right, is that strings have a particular tension in which they would break. Which means although it can provide the tension for the centripetal force, if you try to exceed that tension, the string will break. So this question, we're expected to go and find the maximum speed the ball can reach before the string snaps. Whether y'all give it a shot and try to calculate this with the equations y'all know. So most of you know how to do the first part. We say that the tension in the string is responsible for circular motion. So tension equals to mv squared over r. Right? And we know that when the speed is the maximum speed, that's when the tension is the maximum tension. So we substitute the tension as 50 newtons and get the answer. If you get 12.2, right? If you get 12.2, you understand how to use mv squared over r. Okay, I hope you are not need to copy this because you should be able to do it by yourself. Right, in the next part, I'm going to explain why the string breaks. Well, a very short answer would be, oh, because the tension in the string exceeds 50 newtons, therefore it breaks. But you could explain it with a little bit more detail by saying that to ensure that the ball moves in a circular motion, the string must exert a force on the ball, which also means that the ball exerts an equal opposite force on the string in the opposite direction. So if I draw the free body diagram of the string, it looks like this. String plus tension in the opposite direction. So this reaction force is what causes the string to break. Right? The string doesn't break because it produces 50 newtons on you, it breaks because there's 50 newtons on him. So the real answer is because the string experiences more than 50 newtons of tension on itself. That's why it breaks. Right? So there's a little bit more explaining to do than what y'all might have thought it was. So the exams are expected to provide as comprehensive an answer as possible. You see 2 marks, you definitely need something more than 1 line. Right? So this would be an example of a 2-mark answer. Of course, if it was just a 1-mark question, you could say, oh, because the tension in the string exceeds 50 newtons, when the ball speed is more than 12.2 newtons per second. Alrighty. So, anyone has the topic finished? Okay, let's quickly do it. Alright, so now we need to draw the direction or the trajectory of the ball when the string snaps. So let's say the string snaps at the right side of the circle, exactly at the, well, this is the east direction. East, right? Yeah, east direction. So the string snaps here. Of course, since there's no more resultant force, the object moves off in a straight line. That would be what would happen. Right, and it moves off with 12.2 meters per second, constant speed. Do you get the gist of the idea? So, one more last example before we call it a day. Not enough. This one? Okay. Alright, most of it we done. The last example that we're going to go through is also of circular motion, but now we're going to change up the last question a bit. Instead of moving in a horizontal circle, I now suspend my board. It's still moving in a horizontal circle, but now the tension is no longer in the direction of the center anymore. As you can clearly see, right? The tension is no longer in the direction of the center of the circle. So how now? Right, trigonometry, that's right. So we need to find out which part of the tension is causing the circular motion and which part isn't. So for an object to be moving like this, there's actually two forces acting on it, tension and weight. And part of tension, which is what we say the resultant force of tension and weight, that's going to be the resultant force acting on the object, which is keeping it moving in a circle. Of course, if we call this the x-axis, the sum of forces in the y-axis must be 0, right? Because my object neither accelerates upwards nor downwards. So this must mean that whatever tension is left in the y direction must be able to balance the weight. So we can write this equation down. T cosine theta equals to the weight. The upward tension balances the downward weight. And we can write down another equation for circular motion. The centripetal force, or the net force in the center direction, must be whatever is left, which is T sine theta, and that must be our centripetal force. So again, tension is contributing to the centripetal force, but not all of it, only some of it. In particular, the x component. The y component is used to balance the weight. Okay, so this part I didn't type out in the slides. You're supposed to find the value, or not value, you're supposed to find an expression for tension without theta. Right? That's what the question was. Find an expression for the tension. Since we're not doing any calculation, and we need to solve these two equations simultaneously, how would you get rid of theta? Right? It's a simultaneous equation, but one has cos theta, one has sin theta. You need to be able to get rid of cos theta and sin theta. Wow, seriously, you all are too smart. Yes, you can square both sides, and then you have cos square theta plus sin square theta equals to 1. Then you'll be left with the tension. So you all can write that down in your notes anytime you know, so I'm sorry. I want to solve these two equations without theta. Of course, for the horizontal direction, the centripetal force becomes mv squared over r. Right? So I will be able to find t in terms of m. No need m. I'll find it in terms of v and r. And if I wanted to find theta, that means I want to get rid of the tension, I can then solve it the other way, take one divided by the other, the y-axis equation divided by the x-axis equation, and obtain tangent theta equals to v squared over rg. So it depends on what you want to find. There's many ways to solve simultaneous equations, right? You got two unknowns. Sometimes you want to solve for x, sometimes you want to solve for y. So in this case, you can either solve for t or solve for theta. So the question asks you to solve for t. So if you were to solve for theta, you would get this. So the reason why I wanted to bring this up, tangent theta, is to help you relate this circular motion, right, to your real life experience of twirling objects. So you know somehow when you twirl the object, right, if you twirl it faster and faster and faster, the object would tend to lift itself up. And then the angle theta will become larger and larger and larger. But you know the speed is very fast as well, right? So this is our real life experience. And if our real life experience in physics is true, they must agree together in equations, right? So think about it. Tangent theta equals to v squared over rg. If I were to increase my speed, then theta must increase as well, right? So according to the equation, if I increase my speed, theta must increase as well. So if I try to throw my object faster and faster, you'll find that it will lift up, making a bigger cone than before. So that's actually something we expect as well. So what I'm trying to say is circular motion is correct, no? Yeah, the physics is correct. Our real life confirms it. Right? That's how science works. Our real life ought to confirm experiments. An experiment ought to confirm any theory that we have. Okay, I think there's another lecture coming in. So I will see you all next lecture, and you can ask me questions any you have after the lecture, or you can email me directly. I'll be happy to tutor my class now, so can't stay for long. Alright, have a nice Friday and the weekend, and all the best for your performing sports and whatever.